So if I try to do what is known as a generalized steady state analysis, so we started with this. Steady state analysis of a general converter. So there are two subintervals in general. Of course, there are a number of intervals in each cycle. So the number of intervals is equal to the pulse number. So for the circuit that we have studied till now, I mean there is only one circuit that we have studied, that is 6 pulse circuit. So there are only 6 intervals in one cycle, and in general, of course, I mean there is one more converter which is used in practice. Of course, the practical converter is not 6 pulse converter, it is a 12 pulse converter. So it will be P is equal to 12, so 12 intervals per cycle. So in each interval there are 2 subintervals irrespective of the pulse number. Okay. So the 2 subintervals, I mean this was already mentioned in the last class. So I will just repeat these 2 points. 2 subintervals are there. The first subinterval is from alpha by omega O to alpha by omega O plus T1. So this corresponds to conduction of M plus 1 valves. And the second subinterval starts from alpha by omega O plus T1, and it goes up to alpha by omega O plus uppercase T with a subscript 1. So this corresponds to conduction of M valves. So T1 by definition is the period of the AC side waveform T. So if it is 50 hertz, T is 20 milliseconds divided by P, T by P gives T1, and T1 can be somewhere between 0 and uppercase T1. Okay. So what we do is we try to take the state variables in the first subinterval as x1. So in the first subinterval, so I presume you are familiar with the word state variable, state vector. So state vector is not unique, but the size of the state vector is unique. That is the point. So in the first subinterval, the state vector is say denoted by x1, and in the second subinterval, state vector is x2. So it so happens that more number of valves actually conduct in the first subinterval. So the size of x1 is greater than size of x2, and it is greater by 1. Okay. So if I take x1, x1 is represented by a column matrix or a column vector. So I say that the size of x1 is n plus 1 cross 1, where n is some positive integer or some non-negative integer. Then x2 is of size n cross 1. So I already mentioned that the state variables in x2 are already there in x1. So state variables in x2, x2 is the state vector. So there are n number of state variables in the state vector x2. So these state variables in x2 are in x1. That means there is one state variable in x1 which is not there in x2. Okay. So there is one state variable in x1 which is not in x2. So, this one state variable which is in x1 and not in x2 is nothing but the current in the outgoing valve. So, the outgoing valve current is the one which is not in x2, but in x1. Okay. So, what we will do is we will try to just analyze these two subintervals. So, in general I can write these equations governing the circuit in the two subintervals as linear time invariant equations. So, I think you are familiar with the representation of a linear time invariant equation in the form of equations, differential equations, the two a set of first order differential equations. Okay. So, if I write only first order differential equations, there are n plus 1 first order differential equations, n plus 1 scalar first order differential. So, I write a vector differential equation. So, it will be dx1 by dt is equal to a constant matrix A1 times x1 plus u1. So, u1 is the forcing function or the input. So, in our case we have some sources on the AC side, DC side, voltage sources, current sources. So, that can come in u1. Okay. So, this is the equation for the circuit in the first subinterval. So, the first subinterval is applicable from alpha by omega O less than or equal to t less than or equal to alpha by omega O plus t1. Similarly, if I take the second subinterval is also a circuit and it is governed by a linear time invariant equation. Sorry, dx2 by dt is a2 x2 plus u2. So, in general this u1 and u2 are functions of time. So, if I just now said that they can be the AC side voltages, they are functions of time because they are sinusoidal functions of time. So, this is applicable from alpha by omega O plus t1 to alpha by omega O plus uppercase t with a subscript 1. Okay. So, if I take A1, I said A1 is a matrix. So, what is the size of this matrix A1?
n plus 1 cross.
Yeah, it is n plus 1 cross n plus 1. If I take u1, what is the size of u1? N plus 1 cross 1, it is a column vector. Then A2 is also a square matrix. So, it is n cross n and u2 is n cross 1. Okay. Now, how do we solve this equation? Now, this is a linear time invariant equation, solution is well known. See, I am assuming that you know the solution of this equation. Suppose x is a vector, column vector. Suppose I have a linear time invariant equation in the form of first order vector differential equation. Dx by dt is equal to Ax plus u of t. So, this is a linear time invariant system and it has one more speciality. It has one more speciality. See, it is not just linear. See, time invariant means A is not a function of time. Okay. So, if A is not a function of time, I mean it is not only linear, it is time invariant also. So, the solution of this is, so how do you get the solution of this? See, we usually start with some value of x. Solution means the expression for x as a function of the independent variable time. Time is the independent variable. So, okay, let me say what is a solution first of all. Solution means x as a function of time. Okay. So, what we normally know, I mean in many problems, is the value of x at some instant, say t naught. So, we call this as the initial value or the initial condition. So, we write the solution in terms of this initial condition. So, the word initial means we can get the solution only for t greater than t naught, that is what we mean. Okay. So, most of the problems that we come across, we are not interested in the solution that is a solution for t less than t naught, only for t greater than or equal to t naught. T equal to t naught we already know. So, for t greater than t naught, what is the solution? So, for t greater than or equal to t naught, the solution is x of t. So, what is the solution? Are you familiar with the solution of this linear time invariant system? Yeah, I can write this as exponential of a into t minus t naught into x of t naught plus exponential a t integral. Now, we integrate from t naught, upper limit is t, exponential minus a tau u of tau d tau. So, this is the solution of this equation dx by dt equal to ax plus u of t. Okay. Now, can we get the solution of equation 1 and 2? So, since I know the general solution of a linear time invariant system, so 1 and 2 are linear time invariant systems which are applicable for the two subintervals. So, if you look at the equation that for which we have the solution, instead of x I have x1, instead of a1, instead of u1, that is all. So, I have the solution. So, I will write it as solution is x1 of t is equal to exponential a1. Now, I do not have t naught now. What is there in place of t naught? Alpha by omega o is there in place of t naught. Okay. So, the solution is exponential of a1 into t minus alpha by omega o into x1 of alpha by omega o. So, I assume that the initial condition is the value of x1 at alpha by omega o. So, that is the instant of starting of the first subinterval. Okay. Then the second term, see the first term is due to the initial condition, the second term is due to the input. So, exponential a1 t integral from alpha by omega o to t exponential minus a1 tau, tau is a dummy variable, okay, into u1 of tau d tau. And this is applicable only from alpha by omega o to what? See, we are writing the solution for the first differential equation which is applicable for the first subinterval. So, first subinterval is only up to alpha by omega o plus t1. Similarly, for the second subinterval, the solution is x2 of t is exponential a2. Now, the initial condition is at what time? So, it is corresponding to the initial instant of the second subinterval, that is alpha by omega o plus t1 into x2 of alpha by omega o plus t1 plus exponential a2 t integral alpha by omega o plus t1 to t exponential minus a2 tau u2 of tau d tau. So, this is applicable from alpha by omega o plus t1 to alpha by omega o plus uppercase t with a subscript o. So, let me call the solution in the first interval, I mean this equation giving the solution as equation 1, and this equation which is giving the solution in subinterval 2 as equation 2. Now, I said that there is one state variable in x1 which is not in x2, and that state variable is the outgoing valve current. Now, there is no loss of generality if I assume that this outgoing valve current is the last element of x1. There is no loss of generality, I can keep it anywhere. Okay. So, without loss of generality, let the outgoing valve current be the last element of x1, and this is not there in x2. So, it is only in x1. So, let it be the last element of x1. So, what is this value of outgoing valve current, which is nothing but the value of last element of x1 at the end of the first subinterval, that is alpha by omega O plus T1. What is the value of this last element of x1 at alpha by omega O plus T1? 0. So, because the current becomes 0 at the end of first subinterval. So, how can I write this in terms of x1? See, x1 contains many elements. I am just saying the last element is 0 at the end of first subinterval. So, can I write it in terms of x1? So, I will not try to split x1 and x2 into individual state variables. So, I will use x1 itself without splitting x1 into individual state variables. Can I write this condition in the form of an equation? Yeah, pre-multiplied by a row matrix. So, I will write this as C into x1 evaluated at alpha by omega O plus T1 is 0, where C is where C is, what is the size of C? Obviously, it is a row matrix. So, one row columns n plus 1, because x1 is having n plus 1 rows. Then what are the elements of C? So, I can write C as, so I will write this as, so just to differentiate between 0 and a matrix which is a 0 matrix, I will just put a subscript 1, O1, O with a subscript 1 in and 1, where O1 is a 0 row matrix. So, where O1 is, what is the size of O1? 1 cross n 0 matrix. So, is that okay? So, let me call this equation as equation 3. Now, suppose I take x2, all elements of x2 are also in x1, all elements of x2 are in x1. Now, if I retain the same order of these elements in x1 and x2, if there is also no, I mean again there is no loss of generality if I maintain the same order, then can I relate x2 at the beginning of second interval and x1 at the end of first subinterval? Can I relate x2 at the beginning of the second subinterval? See, x2 is defined only for second subinterval and x1 is defined for first subinterval. So, can I relate x2 at the beginning of first subinterval and the value of x1 at the end of, sorry, I will repeat, x2 at the beginning of the second subinterval and x1 at the end of first subinterval. So, what essentially what I am trying to say is, can I relate x2 at, see this beginning of second subinterval is same as the end of first subinterval. So, it is nothing but alpha by omega O plus T1 and x1 at alpha by omega O plus T1. So, how these two are related? Yes. So, what we will do is, we will take up special cases and try to find what is x1, what is x2, what is a1, what is a2, what is u1, what is u2 for all the special cases. We will consider some special cases. Okay. Say now I am assuming that you have a circuit. If you have a circuit, there is no unique way of selecting the state variables of the circuit, but the number is fixed. Okay. What I am only saying is let one of the state variables in x1 be the outgoing valve current. That is the only restriction. I am not putting any restriction right now on the other state variables. So, there is no unique way of saying what is the set of state variables, but I only put one restriction. One of the outgoing valve currents, let it be an element of x1, that is all. Okay. We will come to that. So, we will try to find answers for what can be possible x1, possible x2, a1, a2, u1, u2. So, how are these two are related? Okay, I will say that pre-multiply by some matrix D, okay, where first of all what is the size of D? See, x2 is having n elements. So, the number of rows in D should be n. x2, what is the size of x2? See, just go back to the previous one. What is the size of x2? Look at the size of x2. Oh, I didn't, I mean, I mentioned in the last class. Yeah. x2 is n cross 1, x1 is n plus 1 cross 1. So, D is n cross n plus 1. And what should be D? What should be D? I mean, what are the elements of D? What are the possible values for the elements of D? Huh? Diagonal 1, rest all 0. So, can I say that it is equal to an identity matrix? So, I will call this identity matrix as I1. Then I already have a 0 matrix O1. So, can I write this as O1 transpose? O1 is of size 1 cross n, O1 transpose is of size n cross 1. Okay. But what is the size of I1? I1 is identity matrix n cross n. So, it is n cross n identity matrix. So, let me call this equation as equation number 4. If I take the first subinterval, it starts at alpha by omega O, the value of x1 at alpha by omega O, and if I take x2 at alpha by omega O plus T1, the end of the second subinterval. Now, at this stage, it seems, I do not know whether it seems that the two can be related.
Yeah.
It seems. Now, what I will do is I will not try to prove this, but I will just make a statement and verify later. So, right now it seems, that is all. I mean, you can't prove it as it is with the current information. So, I will make a statement without proof, we will verify that it is correct later. So, I will say that this is f times x2 at alpha by omega O plus T1 plus g. So, where f and g have appropriate sizes. So, what is the size of f? Size of f actually comes from the size of x1 and x2. The number of rows should be the number of elements in x1, that is n plus 1. Size of x2 is n, so it is n plus 1 crossing. And g, okay, what is g? What is the size of g? That should be obvious, right? What is the size of g? Say, when I am adding two elements and saying it is equal to a vector, both elements should be vectors, column vectors. So, size of g is same as size of x1, n plus 1 cross 1. Okay. So, let me call this equation 5, which I have just mentioned without proof. We will verify it later. We will take this for granted. Phi is just taken for granted, which is mentioned without proof. We will verify that phi is actually true. Okay. Okay. Now, we have so far 5 equations. Now, I take equation 3, and get an expression for x1 evaluated at alpha by omega O plus T1 using equation 1. Can I do that? See, the first equation gives the expression for x1 from alpha by omega O to alpha by omega O plus T1. So, I can get the expression for alpha by omega O plus T1 using equation 1. Okay. So, that let me do that first. So, from 1 and 3, what I do is I take the equation 1, just take the solution. So, it is x 1 at alpha by omega o plus t 1 means wherever there is t, I have to replace that by alpha by omega o plus t 1, that is all. Okay. So, the right hand side, if you look at the right hand side, the first term is exponential a 1 into t minus alpha by omega o. So, replace t by alpha by omega o plus t 1. So, what? So, the result is exponential of a 1 t 1, a 1 t 1, that is the first term, into x 1 evaluated at alpha by omega o. There is one more term plus there is a there is a factor c there, plus c into exponential a 1. So, in place of t I have t minus sorry, in place of t I have alpha by omega o. So, if the letters are too small to read, please let me know. Are you able to read that? Okay, alpha by omega o plus t 1 into integral, the lower limit is alpha by omega o, the upper limit is alpha by omega o plus t 1 exponential minus a 1 tau u 1 of tau d tau. So, this is equal to 0, that is equation 3, that is what is equation 3. Okay. So, let me give a number for this, let me call this equation number 6. Now, take equation 5. If you look at the right hand side of equation 5, there is x 2 evaluated at alpha by omega o plus uppercase t with a subscript 1. Now, I can get an expression for this value of x 2 using equation 2, because this is the last instant of the second subinterval. So, I can use equation 2 to get the expression for this x 2 at alpha by omega o plus t 1 in equation 5. So, from equations 5 and 2, so from 5 and 2, so 5 says x 1 at alpha by omega o is equal to f into x 2. So, x 2, if you look at equation 2, exponential a 2 into, so wherever again there is time, replace it by alpha by omega o plus t 1. So, if I do that, what do I get? Exponential a 2 into what? Yeah, uppercase t 1 minus lowercase t 1. Okay. So, this multiplied with x 2 at alpha by omega o plus t 1 plus there is one more term f into exponential a 2 at alpha by omega o plus t 1 into integral alpha by omega o plus t 1 to alpha by omega o plus t 1. So, integral of exponential minus a 2 tau u 2 of tau d tau plus what? Plus g. Okay. So, let me call this equation number 7. Now, what I will do is I will use this equation 7 and there is one equation equation 4. So, I will just replace x2 at alpha by omega o plus t1 by d into x1 at alpha by omega plus t1 using equation 4. See, what I am trying to do is I am using equations 4 and 7 at the same time and get rid of x2. See, there is one x2 in equation 7 in the first term on the right hand side. So, I will write that in terms of x1. So, from 4 and 7, x1 at alpha by omega o is equal to f exponential a2 into t1 minus t1 into x2. So, x2 is now x2 at alpha by omega o plus t1 from equation 4 is d into x1 of alpha by omega o plus t1. Which one? Now, I am just using equation 4 here, 4 and 7 right now. Is that okay? This is okay up to now. It's, if there is any error, let me know. Then plus f exponential a2 alpha by omega o plus t1 integral alpha by omega o plus t1 to alpha by omega o plus t1 exponential minus a2 tau u2 of tau d tau plus g. Okay, I mean, it appears I am doing too many manipulations, but I will ask you why I am doing this. I mean, once it becomes a bit clear. Okay, so let me give some number for this also. Equation number 8. Now, what I will do is again use equation 1 and solve. I mean, get an expression for x1 at alpha by omega o plus t1 in the first term on the right hand side. So, from equation 8 and 1. So, from 8 and 1, okay. So, what I get is x1 at alpha by omega o. See, finally our intention is to get solution. Please note, finally our intention is to get solution, but the question is what are the quantities that are already known and what are the quantities that we need to determine. Obviously, we need to determine x1 as a function of time, x2 as a function of time, but are there some quantities which are unknown? That is the question. Okay, we will answer that question. Okay, let me just do one more step and try to see. So, it is f exponential a2 t1 minus t1 d. Now, substitute for x1 using equation 1. So, what I get is exponential a1 what? If I use the first equation a1 t1 into x1 at alpha by omega o, that is the first term, plus f exponential a2 t1 minus t1 d, and the second term is exponential a1 into alpha by omega o plus t1 into integral alpha by omega o to alpha by omega o plus t1 exponential minus a1 tau u1 of tau d tau. So, this is nothing but the first term in equation 8. Up to this is first term in equation 8. So, the second term in equation 8 is written as it is, plus f exponential a2 alpha by omega o plus t1 integral alpha by omega O plus T1 alpha by omega O plus T1 exponential minus A2 tau U2 of tau d tau plus G. So, I will give one number for this 9. Now, in equation 9 you see that there is x1 at alpha by omega O on the left hand side and there is also x1 at alpha by omega O in the first term on the right hand side. So, I will just get an expression for x1 of alpha by omega O. So, I will say that x1 of alpha. So, bring the first term on the right hand side to the left hand side, first term on the right hand side of equation 9 to the left hand side, and then I get a factor. So, if I pre-multiply by the inverse of that, what I get is x1 at alpha by omega O is equal to I. So, I already used I1 for some other identity matrix. Now, I use I2. It I mean we will show that both are not same, they are of different sizes. So, I2 minus f exponential A2 T1 minus T1 d exponential A1 T1. Now, first of all, you notice that f into exponential of A2 T1 minus T1 d exponential of A1 T1 is a square matrix. This coefficient of x1, see in equation 9, the first term, equation 9 first term, the coefficient of x1 of alpha by omega O is a square matrix. That is a square matrix. Okay. So, the square matrix inverse into what? The rest of the terms on the right hand side. So, the rest of the terms are the second term, the third term, there are 3 more terms. Okay. So, let me write all those terms. F exponential A2 T1 minus T1 d exponential A1 alpha by omega O plus T1 alpha by omega O alpha by omega O plus T1 exponential minus A1 tau U of tau, sorry, U1 of tau d tau plus f exponential A2 alpha by omega O plus T1 integral alpha by omega O plus T1 alpha by omega O plus T1 exponential minus A2 tau U2 of tau d tau plus G. Is this okay? So, we call this as say equation 10. Okay. So, I will just do one more step and then see why we do all these manipulations. By this time, if you are able to guess, very good, otherwise let us discuss. Now, we have used an identity matrix I2. What is the size? I2 is an identity matrix. I1 was n cross n identity matrix. This I2 is what is the size of I2? N plus 1 cross n plus 1.
How are we getting this?
Oh, equation 10.
Size of I2.
Size of I2. See, left hand side is having n plus 1 elements, x1.
Okay. Also, you said that this is a square matrix.
Yes.
F e power 8.
Yeah, that is from equation 9.
Yes.
See, left hand side is x1. The first term on the right hand side also has x1.
Okay.
So, that means this coefficient should be square matrix. See, the other possibility is scalar,
Yes.
but it is not a scalar.
Yes.
Okay, say, okay, let me first
Got it.
make a few points. Say, I am assuming many things. For example, I presume all of you know what is matrix exponential. I mean, I didn't even make a mention of that. I presume that you know. I mean, you are familiar with matrix exponential? Okay, let me see. Suppose I have a matrix M. Okay, so if M is a square matrix, exponential M, as long as M is square matrix, that is a restriction. M is square matrix. What is exponential M? By definition, it is given by this series. So it is similar to the scalar exponential. You know, it is sigma M raised to k divided by k factorial, and k takes values from 0 to infinity. And you know what is M raised to k? M raised to 1 is M, M raised to 2 is M into M, M raised to 3 is M into M into M. What is M raised to 0? Identity matrix. By definition, M raised to 0 is identity matrix. Okay. So this is the definition of matrix exponential. So if M is a matrix, square matrix, then exponential of M is also square matrix, because you look at the terms. See, M raised to 0 is identity matrix of the same size. M raised to 1 is just M. M raised to 2 is again a square matrix of the same size as M. Okay. So exponential of the matrix is also a square matrix. Okay. Yeah. Now let me finally write one more equation. So what I will do is, I will use this equation 10 and substitute this in equation 6. See, equation 6, if you notice, the first term has x1 at alpha by omega o. So now I have an expression for x1 at alpha by omega o from equation 10. See, equation 10 is essentially giving the expression for x1 at alpha by omega o. So I substitute this expression for x1 at alpha by omega o in 6. So from 6 and 10. So the first term of equation 6 is c into exponential a1 t1. C exponential a1 t1 into x1 at alpha by omega o. So I write this as I2 minus f exponential a2 t1 minus t1 d exponential a1 t1 inverse into f exponential a2 t1 minus t1 d exponential a1 alpha by omega o plus t1 into integral alpha by omega o to alpha by omega o plus t1 exponential minus a1 tau u1 of tau d tau plus f2 f exponential a2 into alpha by omega o plus t1 into integral alpha by omega o plus t1 to alpha by omega o plus t1 exponential minus a2 tau u2 of tau d tau plus g. So this is the first term of equation 6. If you look at equation 6, so this is the first term of equation 6. The second term written as it is. So the second term of equation 6 is on the left hand side, c exponential a1 alpha by omega o plus t1 alpha by omega O to alpha by omega O plus T1 exponential minus A1 tau U1 of tau d tau. This is equal to 0. Now, why I did all these manipulations? Now I ask the question, what is the purpose of doing all these manipulations? My intention is to get the solution. Yeah, I didn't want to spell out the answer, that's why I did. I mean, maybe I thought you will guess or find out why I did all this. Okay, see, okay, let me give a hint. What are the known quantities? What are the known quantities? Let us start with the differential equation first. If you take the first order differential equation, what is known there? A1, A1 is known, U1 is known. See, the U1 is known because you know what is the voltage source or current source. Okay. Then A2 is known, U2 is known, then C is known. Then what about D? D is also known. Then I mean, now I will say that, see, when it comes to the equation relating x1 at alpha by omega O and x2 at alpha by omega O plus uppercase T1, there are two matrices F and G. Okay. So, that equation was just assumed. So, I will make one more statement and prove it later that F and G are also known. Okay. So, F and G are known. Now, there are a few other quantities that come. For example, omega O, it is known. See, if it is 50 hertz, it is 100 pi, if it is 60 hertz, it is 120 pi, that is also known. Okay. Then what else we know? There are a few more terms. Alpha is there. Now, I assume that alpha is also known. For a given value of alpha, I am doing the analysis. Then there is an uppercase T1, that is also known. All these are known quantities. See, uppercase T1 is nothing but the total period divided by P. Total period is known, pulse number is known. Now, there is one more quantity which is lowercase t with a subscript 1. That is not known. Okay, that is the answer. So, the unknown quantity is lowercase t with a subscript 1. Now, why do we need this lowercase t1? See, if you look at the solution, say solution is given by equations 1 and 2. It is given by equations 1 and 2. Now, T1 is deciding when the first subinterval stops. So, I should know when it stops. See, when is equation 1 applicable? Up to what time it is applicable, I should know. But, okay. So, I should know, but I mean, as of now, I don't know. I have to solve for it. So, how to solve for it? So, all the manipulations done so far is for solving for T1. So, if you look at the last equation, so let me give a number for that. So, the last equation was this equation 11. So, in equation 11, it is a long equation, but everything other than T1 is known. So, solve for this unknown quantity T1 using equation 11. So, equation 11 is not a vector matrix equation, it is a scalar equation. So, it is just one nonlinear equation, it has to be solved for T1. So, solve equation 11 for T1. So, how do you solve? Yeah, use any numerical method. Newton's method, Newton-Raphson method is one of the, I mean, obvious choice for a method. Okay. Of course, calculator it is tough. Calculator will not allow matrix exponential such things. Okay. So, it is not ruled out. Calculator is ruled out. So, one has to use a computer. I mean, try to write a short program for any numerical method. Newton-Raphson is, all of you are familiar with Newton-Raphson, I guess. It is used for power flow. So, one can use, for example, Newton-Raphson method and solve for T1. Now, our objective is not solving T1 alone. Our objective is to get the solution. So, then what? If T1 is known, then can I get the solution directly? See, go to the solution. What is the solution? Equation 1 and 2. Oh, sorry. Equation 1 and 2 are solutions, but they are solutions provided everything on the right hand side is known. M, where is M?
Number of switches that are
No, M is nowhere coming in the,
they are not in the equation.
no, we will look at the size of M for different cases. M is right now not known. It depends on whether it is 2 and 3 valve conduction mode, 3 and 4 valve conduction. That is not known now. That is itself also not known. Okay. Now, what we normally do is first assume something. Suppose it is 2 and 3 valve conduction mode. Try to find an answer. If you get an answer, it is 2 and 3 valve conduction. If you don't get an answer, it is not 2 and 3, try something else. See whether it is 3 and 4. Again, if you get a solution, that is the answer. Otherwise, it is not the answer. So, again, it is only by trial and error we can make out whether it is 2 and 3 or 3 and 4.
But for like 12 pulse,
Yeah, that I mean that is even more complicated. Let us first concentrate on the simple case. Okay. So if 1 and 2 are solutions, what is required? Yeah, to use this equation 1, we should know all things on the right hand side. So A1 is known, A1 is known, but what about x1 at alpha by omega O? So that is the only thing that is required. U1 is also given. Okay. So x1 at alpha by omega has to be determined. So how to find that? Which equation will give me x1 at alpha by omega O? Equation number 10. Because if you look at 10 has something which is I mean having all known quantities on the right hand side. Okay. So, but for using 10 you need T1 and T1 is obtained from 11. Okay. Once you know T1, then obtain x1 at alpha by omega O using 10. Okay. Then from this use can I just use equation 1 for solution in first sub for obtaining the solution in first subinterval? Is that okay? If I just know x1 at alpha by omega O, once I know this, can I just use equation 1 and solve for x1 in the first subinterval? Then in the second subinterval, I want x2. So what is unknown on the right hand side? x2 at alpha by omega O plus T1. So how to find that? That is the only unknown quantity on the right hand side of equation 2. So how to get x2? So it is nothing but equation 4, because right hand side we know x1 at the end of first subinterval. So get the value of x2 at alpha by omega O plus T1 using 4.
also equals x1 at alpha by omega.
Yeah, okay. Now that x1 is obtained from the previous step. See, when I say solution means getting the expression from the starting to the ending point of the first subinterval. Okay. So then compute x2 at alpha by omega O plus T1 using 4. Then use equation 2 for obtaining solution in second subinterval. Obtaining the solution in second subinterval. Fine. So it requires initially the solution of a nonlinear algebraic equation, equation 11, to solve for this unknown quantity T1. From that everything else follows. So how exactly to use this in the special cases, we will see that in the next class.